Hello and welcome to this mini course on entanglement, ensembles, decoherence, and quantum measurement. And in this series of short videos, I'm going to be talking about some things that I wish that I understood when I first learned quantum mechanics, but it actually took me quite a while to be exposed to these various topics and to kind of fully understand what I'm going to tell you about. So I want to start in this video with a setup, and I want to review how we describe multipart systems in quantum mechanics. And so the idea is we want to imagine, let's draw a picture. Here's a system, and the system has two parts. Maybe these are two different spins, or they could be two different molecules. And the idea is that we're going to have some Hilbert space that describes all of the states of the first quantum system and some Hilbert space that describes the various states of the second quantum system. And these could have different dimensions. And so what we're going to assume is that we have some basis for the first one, and the basis elements are going to be labeled by n, and we have some basis for the second one, and I'll use capital N to label the states, the basis states of that system. And so the general state of the first system is going to be some linear combination of those basis elements, and so we have a coefficient for each one, and then the basis element. And similarly for the second part of the system, the general state is going to be a sum over all those basis elements and a coefficient, and then the basis element. So how do we describe the general state of the combined quantum system? And so the Hilbert space for that combined quantum system is what's called the tensor product of the two previous Hilbert spaces. Okay, so the Hilbert space is a tensor product, and that sounds fancy. And there's actually a fancy notation that we use to describe that Hilbert space, and that is this fancy multiplication symbol. But it's actually very simple to describe what this Hilbert space is. And so the tensor product Hilbert space is just defined by specifying what is the basis for that Hilbert space, and that is going to be indicated like this, or more simply like this. And so the idea is that you can take any basis element of the first Hilbert space and any basis element of the second Hilbert space, and then you combine those into a basis element for the tensor product Hilbert space. Okay, and so if you have some number of basis elements for the first one and some number of basis elements for the second one, then the number of basis elements for the full Hilbert space is just the product of those two. And so the dimension of the full Hilbert space is the product of the dimensions. And so if I want to describe a general state of the combined Hilbert space, then what I do is just take a linear combination. So I sum over both little n and big N, and then I have a coefficient labeled by these two integers, and then I have my basis element. And so let's just do a simple example where we have our quantum systems as two different spins. So let's say two spins to start with. And so then each part is going to have a basis of just two elements. So we can label those as up and down, and the general state for each part would look like some number times the up plus some number times the down. And I'm not worried about normalization here. If we want to normalize, we can demand that a squared plus b squared is equal to 1. And now the combined system, as we described above, is going to have a basis that looks like all possible pairs. So up, 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 down, down, up, and down, down. And we're going to have a general state for that combined system that is a linear combination of those basis elements. So C1 up, up, plus C2 up, down, plus C3 down, up, plus C4 down, down. And it's interesting that if you think about larger combined systems with more spins, so if we had n spins, then the number of basis elements is going to be 2 to the n, because each basis element is some combination of basis elements for the individual systems, and you have a choice of 2 things for each individual system. So we have 2 to the n basis elements for example, up, 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 etc., and then up, or let's say down, up, up, and so forth. So you have really a lot of basis elements once we start adding quite a few spins. And so one of the things we realize is that when we want to describe the general state of a system with n spins, we're going to need 2 to the n coefficients, and those are complex numbers. And so the amount of information needed to describe a quantum state of n spins actually grows exponentially in n. And so this sort of motivates a question that we're going to ask in the next video, which is, suppose I only care about one of those spins in the context of a system with many parts. How can I describe the information that only pertains to that first spin, or that single spin? And so we'll be talking about that more in the next video.